Hello, everyone, and thank you for coming. Today we have Ann Cow, who has graciously agreed to come speak for us today. She's an executive consultant at the Collinear Group, and she was a senior technical fellow at Boeing, where she worked for 30 years. All right, take it away whenever you're ready, Ann.
Thank you. Thank you for the introduction. Thank you for inviting me. Hi, everyone. I'm Ann Kao. Feel free to write down my email address and two, my personal one and Collinear Group's email address. Feel free to contact me anytime, whether it's questions and thoughts on artificial intelligence or career development, a number of things. Feel free to reach out to me. And you will have the slides after the talk, but I will try to explain things instead of reading through the slides, which is more interesting. Feel free to stop me anytime, but I know this is virtual, that may be hard. So every page has page number, so that's on the lower left. You can write down the page number or just write down your questions. You can get in immediately, ask a question. There'll be plenty of time in the end for questions and discussions. So today I'm going to talk about artificial intelligence and also talk about a little bit about robotics, how it ties into artificial intelligence, and hopefully you will start thinking more about the different areas, hot areas, and uh, maybe it'll help you make some career decision where you like to go after high school. So artificial intelligence, it's a short definition would be it's intelligence displayed by machine. And machine seemingly displays intelligence, mimicking human cognitive functions. So as you can see, I put a lot of wiggle words here, right? Seemingly display intelligence. We don't know if it really has intelligence or not. And it's mimicking human cognitive functions. That's why we call this artificial intelligence. There is a branch people believe in strong AI. What does strong AI mean? You might have read it on newspaper, or they don't necessarily call it strong AI. They believe the machine actually has human level intelligence or even higher level intelligence. And the machine has the ability to apply this intelligence to any problem rather than just one specific problem. Sure, we all know there are plenty of artificial intelligence software, program, robots, but today they're really only solving one specific problem at a time. Very different from human, right? We have one brain. We don't put on different brains to solve different problems. So there's a major difference there. And people believe in strong AI. They believe in the future, or some believe around the corner. Not only the machine is actually with human level intelligence, or even smarter, even higher, and it will become a universal machine that one machine, like human, or even better, solves all problems. And we're so not there. To answer whether machine really has intelligence or not, well, Turing, Alan Turing, uh, he designed a test. Some of you may have heard of Alan Turing. He plays a crucial role in the field of computer science. You can say without Turing, there's not much computer science going on at all. And there are several movies and novels and books about Turing, so you may be interested in checking out some of these. Um, it's fun. So Turing designed this, and he said, let's do a test. How do you know? Let's do a test. And his test is saying, if you can't tell the difference, whether it's a machine performing it or it's a human performing it, then it must have intelligence. Well, that's interesting, right? This gets philosophical. Just because you cannot tell the difference, does that mean it really is the same? This is something you can think of on your own. This gets very involved on the philosophy side. But let's look at how Turing does it. There are many versions implemented on the Turing test. One of the best known ones is called ELIZA. So what does ELIZA do? basically, you can, by the way, you can search ELIZA. There's a Wikipedia page. There are also software you can play with online. And it's a script about doctor visit, specifically more like a psycho analysis kind of visit. So you say hi, Eliza will say hi, and Eliza will say, "What's on your mind?" You say, "Oh, my mother." And Eliza would say, "What about your mother?" Whatever you say, basically Eliza is just spitting back cleverly the relevant part of your sentence and make you believe there's a conversation, but there's really no conversation. You say, "My mother." "Oh, my mother, she she's not feeling well." Then Eliza would say, "What about it?" Oh, then you say a bunch of stuff. "Oh, she has a cold." And Eliza will say, "How is it?" So Eliza is really not telling you anything it understands, but it understands a basic pattern of your language and just keep spitting out and make you feel there's a real conversation while there isn't any, because just spitting out these words. So that's a test. But this is almost like a sarcastic way of saying that. Just because you can't tell there's a difference, whether it's a human behind this saying this or it's a machine, computer, that doesn't mean it really has intelligence. But this is a well known test, and so I'd like to share this with you. But it's important whether you believe strong AI or not, meaning you believe one day machine will be smarter, as smart as human, or even smarter. One machine can solve all the problems human brain is solving plus more. Whether you believe in that or not, AI still brings value to all of us. So I'm gonna talk about just briefly on this page a few different tasks we use AI to do. And there are more, there are definitely more. And on top, I'm just going to go from top, knowledge representation. This is a little bit hard to explain, so I'll explain it shortly a little bit later. Natural language processing, you just heard one example, right? The AI program can figure out the sentence pattern. Whatever you're saying, it gets to the important part and add its own pattern, spit it back out. Of course, natural language processing, there are a lot more examples, a lot more tasks to do. And in today's presentation, I'll have more examples for you on that. There's a reasoning and inference. Very early on, there are programs about doctors can use, and definitely there are later versions today, and some clinics are using. You can say, if this is the case, this is the case, then this is likely the disease. And I'm sure many of you with COVID prevalent uh, have read, if you're sneezing and you're coughing, but you don't have fever, well, that's therefore it's likely a common cold. But if you're sneezing and dry cough and have fever and high, very high temperature, then you possibly have COVID. So the reasoning system will be like programming all these different symptoms and diseases, a lot of this. And some hospital clinics, doctors are using this kind of tool to help them just double check, hope they don't miss anything. And that's one type of application. The planning and scheduling, you can say in order to perform a task, for example, in order for a robot to perform a task, there's steps. How do you do these steps? To move over, to hit the ball over there, for the robot to hit the ball and have a goal, you have to first move the robot, right? It's stepwise. You have to accomplish a lot. And why are you doing that? Some tasks takes longer than others. You can have to take that into account to schedule that. And who's the closest player? Maybe you want to send up that robot to do the task, etc. And speech recognition, many of you, maybe you have Siri at home, you have Alexa at home. That's a version of AI application, AI test. Computer vision, you might have heard people using AI to do facial recognition, and some airport even does that, and etc. So those are very well known um, AI tests. But there are actually more, and you'll hear more right now. And I just mentioned some of this last page. So why does AI all of a sudden become so hot? And because there's successful applications people can relate to. Speech recognition tools is one type, as we just talked about, and successfully discovered image concept of cat face. That's another one. So here I mentioned from unlabeled data. That just means there's no human providing example. This is a cat, this is a dog, this is not. It's rather the machine uh, basic figure out from, say, 6 million these images what seem to represent cats. And that really shocked people. Um, but we're going to talk about the actual constraints, how you can use this type of techniques. And we all have heard and self-driving vehicles, many different automobile companies are developing these and to show up on the road for testing. And broadly speaking, vehicles doesn't have to be just on the ground. And many companies are developing self-flying vehicles. And of course, we haven't seen any because they're not allowed to go up and flying around other than little just a drone. But any real size is not allowed yet. But we all know humans have been in space. That's a self-flying vehicle really to outer space. And these are things really excite people. And also, let's look at there are a lot of examples that in the news talking about how these AI programs or robots really beating experts and winning games. So let's look at some of that. And so AI has been a world chess champion many years ago, 1997. And Deep Blue, IBM's Deep Blue did that. And more recently, somehow more recently, AI beat Jeopardy champion. I don't know how many you play Jeopardy. I'm certainly no good at that. And watch IBM do this, and I have collaborated with the Watson team as well, so definitely familiar with their work. And it actually has a lot of design in it specific to play Jeopardy. People often think, gosh, if it can win Jeopardy, it knows everything. Not exactly. It can take that design capability to solve more problems, but that doesn't mean Watson itself knows everything. So AI also beat Go Champion. That's a little bit less known, but some of you know that. And also Atari video games. I certainly play Atari video games as an early generation of personal computer. There are a lot of great games like Pac-Man. Watch AI play this successfully. Well, that's exciting. But so what, right? This is exciting for us to know that AI can do a lot of things, can make a lot of progress. But some of you are chess players and even Go players. Does that mean, okay, we got a robot, some robot, one or two in the world, can do this well? I'm going to stop playing? No, I don't think so. If you love chess, you love Go, you're not going to give up because they're robots, they're beating world championship. And personally, I'm not a chess player, I'm not a Go player, but I'm a serious bridge player. So some of you may have watched bridge games and you may be interested. I'd love to get you connected to their programs and teaching young people bridge locally in Seattle area. And bridge is something robots do not do well at all. And not for lack of trying. With COVID, and there are tons of online games and many thousands of people attending every day with these online games. This is not gambling. This is just competition. But the robot is about intermediate level player. There are lots of things robots do horribly. Why? It's hard to say. There are many reasons. Partly, bridge game has a lot of psychology. You have partnership, how you communicate, whether it's between robots or human and robots, and how do you observe your opponents. The psychology part, the communication part, far more important than a chess or Go game. So there are research projects on this on bridge, and you can find online as well, but they don't do nearly as well. And the best robot today, they're playing so-called using Monte Carlo tree search. What Monte Carlo tree search means is go ahead, generate all the possible moves as much as the time is allowed, and then pick the one seem to have best likelihood, best probability to be to be a winning move. So that's Monte Carlo tree search. Instead of AI will give you some clever statistic or clever design, which we'll talk about a lot more next few slides, so you understand how this is different. So let's talk a little bit about evolution of AI. So AI really started again very early. This is even before my time, right? And from Carnegie Mellon, MIT, IBM, and started as research. The original type of AI programs are expert systems. Like I mentioned, there are things they use, talk about based on symptom of patients and what are likely to be the disease. They don't use probability. They just say if then else. If that's logic and reasoning. If you have high fever, you have dry cough, and you're sneezing, then you have COVID. Of course, it's not 100%, but doesn't program in these probability early on, just if then else. Or they also have ways to distinguish what likely is a certain type of rock. That's another program. And today you can think about, hey, if you know the humidity is certain level, the temperature is between say 30, 33, 34, and then it will snow. And so these are the if then rules that the system program. It was very useful because it needs to represent all this information. And represent this information is not always easy. And then it can reason all that. But early on, fairly early in the 80s and or so, there are two ways to do AI. One is symbolic processing, the other is neural networks. So today you'll probably hear more about the neural network side, but it's not to say the symbolic processing side is not useful or just the progress is less on the symbolic processing. What is symbolic processing? Exactly like my example, logic and reasoning. You will represent these as facts. You will talk about this is an object, this is an event. What are the features of the object? What are the events? What are the features? And then you start doing this if then else kind of rule. This, or this, and not this. Then this is the situation. So that's the symbolic reasoning side. And what about neural network side? The neural network side is a little harder to explain, but I will try to give you some intuitive explanation. And so think about how the machine will recognize cats or any image. It only knows pixels. The pixels, the brightness, the hue, and all the basic, the color. And it goes down very detailed level. The detail level, you think about, if you look at the screen now, you see Julia and my face. How do you recognize where the face is if you only have pixels, right? First of all, you can't just divide it by, say, 9 boxes and try to figure out. You got to define a much finer grain. And a lot of areas, you don't hit anything. And what if you get unlucky, you cut off in the wrong place? You also don't figure out anything. But if you do it, fine tune it, you have a moving window, very small area, then you start processing these and you start getting feedback. Am I getting something useful? There'll be big blank area that seems to be all background. They're different in colors, but not that different. But then you hit some areas, our face, our head, and all of a sudden this seems to be darker. What if we connect that? So this is roughly how neural networks and nodes are connected. The data for image processing, you usually have overlapping, so you can start figuring out the boundary. Then you figure out the boundary, then you start seeing what's more. What does this boundary tell me? So early neural networks can do all these complicated things, but the attempt is similar. You have more nodes and doing smaller amount of work and try to feed to next level, see if you can understand better. So you start from really low level features. If you can move up, then you can combine some of these features into more meaningful units, then you can start doing better. So that's more the neural networks approach. Not that we're going to record some fact. If you do image analysis with the symbolic reason, it'd be very hard. You're going to have to say, find you have background, then you have foreground people have a head, the head has hair, head has eyes, so all this stuff, and it's a lot harder to do for this kind of application. So then there comes machine learning. So what does machine learning do? The ability to learn. The software, the program can learn, meaning without human explicitly tell it, you did this wrong, let's redo this. Do it different way. I'm going to tell you, do this way instead. But the machine can start improving by doing, repeating itself, doing more and more of these. And how, right? So I will explain that. The name, again, is not new at all, but it started becoming mainstream in late 90s and early 2000s. And the machine discovered these patterns instead of experts create these knowledge base, tell it. That is very appealing because create all this knowledge is very hard. And I will give you even more example on why this is hard. So the machine can discover the patterns and anomalies in the data that experts don't even necessarily know. Another way to think about it, you heard about a lot of the, on the medical side, there are always people studying data, try to find correlation. They don't know this caused that. But if there's a high correlation, then you start looking into it. So this is a similar idea, but use machine to do a lot of often lower level computation, meaning like the bits and color and the pixels and colors and to build up much higher level of tasks that they can do well. And but there's still a challenge for using machine learning. Partly is machine learning still doesn't have common sense knowledge and also doesn't have domain knowledge. So domain knowledge is easier to understand. You are on a robotics team. If you play any kind of robot game, you need to know the rule of the game, right? And that you have to find a way to program in so it knows how does the robot play Go? How does robot play chess? You need to tell it these are the specific rules. And that can be complex. And for some application much more involved than, say, a chess game or a game of Go. The rules are very simple. And the common sense side, that is also very hard. Today or this weekend, start thinking about if you are building a robot, just go from your desk to go get mail in a mailbox. You've done it enough times, probably. And how would you tell the robot to do that, right? The robot goes to the door. This door closed. Does it open from the left, from the right? When the door opens, the robot needs to step back. Otherwise, you hit right at the door, you're going nowhere. Think about every little the common sense we already have just moving around. We don't want to hit things, we don't want to block things, and it goes outside. What if it's dark? Then it needs to generate light or find light sources. Otherwise, even when the robot is smart in visualize things, doesn't see anything. So there are a lot of common sense involved. And to perform a real task, even with machine learning, when it doesn't have common sense, when it doesn't have domain knowledge, it's still hard. Imagine instead of recognizing cats, I want to program the software, go find legs of the cats. Well, you and I know cats usually have four legs, and we also probably know in the photo, you don't typically see all four legs, you see two, three. So if you find all four, gosh, you don't have to go any further. But if you don't tell a machine any of this, it's going to waste a lot of time doing useless stuff. And so this is just some example to help you understand, even with machine learning, it's still hard. And I will explain more different types of machine learning. So in early 90s, AI hit AI winter. I was hired by Boeing in 1990. My official job title was AI specialist. So today, most people in Boeing didn't even know. Boeing started an AI center late 80s. Boeing thought would train us. We are the AI associates. We'll propagate. We'll go train more people doing AI. So the whole company will be armed with AI, and we're set. Well, guess what? That never materialized. We hit AI winter because on the symbolic reasoning side, it's hard to represent all this knowledge. There's a lot of inconsistency. There's incomplete knowledge. It's a very daunting task. Humans are very good in processing incomplete, inconsistent knowledge. Say you and your friend say you would go to college. You go to college, gosh, the college campus is huge. How do I find my first class? I'm looking at math, I'm not sure. I asked my friend. My friend said, okay, you go past the stop sign, you have this building is blue, and there's an empty area, and that's your building, and you go in. Okay, you walk there. Well, there's a stop sign, but then there's a light, a traffic light. My friend didn't tell me that. Well, the building is not blue anymore. Maybe it's repainted. You're very good in reasoning all this and get this incomplete and even incorrect knowledge, but you're able to use your common sense plus some knowledge and make a judgment to continue. But if you're robots, you give it all this incorrect information, it's gonna just stand there unless you have other clever way to tell it to continue until say it hits so many errors or so many things wrong. Otherwise, it's just going to be very hard. So on the reasoning side, it's very hard to use this kind of knowledge. They're incomplete, inconsistent, hard to build up, and they are actually projects spent over 10, 20 years trying to build up and was not very successful. Um, on the connection, the neural networks machine side, we were promised there will be special purpose machine just to do this kind of reasoning, and therefore it can do it faster. But that never happened. Partly it's because there's no market. If you build a special purpose computer just for that, how many do you think will sell? And there are many reasons. This never materialized. But how did we get back to AI being so good and so much in the center of everything? A lot is due to huge growth with machine learning. So why did machine learning all of a sudden get so much better? Partly is data, realizing data is a new oil. You may have heard the slogan. If you just go with the data you have, you can do a lot better. And the storage is getting better, a lot cheaper. It can handle a large amount of data stored. computing power. There's a graphical processing unit, which is very good in processing mathematics. The cloud computing, you can tap into different computing resources to compute a much larger problem than you would be able to just on your own machine. And of course, communications, all that is getting a lot better with cloud computing built on these better, faster internet communications. And so you can compute more and you can solve better problems and bigger problems. Also, the different classes of machine learning, the newer classes start coming out. So before these new algorithms came out, typically when we talk about machine learning, we were saying supervised and unsupervised learning. So what are they? The supervised learning is we human give the machine examples. These are images of human. These are images of cats. These are images of dogs. And this is where we think the product has a defect. If there's spots here, if there are unevenness, so these are supervised learning. What's unsupervised learning? That is, without human provide examples, the machine will just look at what seems to be unusual. For example, spam email. I can tell you if certain type of groups send out these, it's spam. But the machine can figure out, gosh, some of the email are unusual. Why? There's so many symbols. If I write an email to you, I will not use all these symbols, but often the spam email will have a lot of symbols to try to get your attention. There's an unusual number of symbols. And that could be a flag telling you there's something unusual about it that's worth looking. So that's unsupervised learning. But there are two new different types. One is reinforcement learning. Again, the original concept wasn't all that new, but to make it a mainstream is very recent. Basically, the software, the machinery can understand feedback from the environment. The easiest way you can think about is a robot. If a robot hits a wall, it can't go any further. You need to back up. You got that feedback. You can't be stuck there. You need to back up, change direction, and go a different direction. So that's the concept. It's different from supervised or unsupervised learning. It has certain mechanism to self-correct. But of course, that's not to say all problems can be solved that way, right? If you want a robot, a AI program, help you decide what is the stock that will really go up. Well, there's no feedback that direct, right? Do you look at the stock go up in few minutes, in few hours, in a few days or months? This is very hard. What is the feedback? Not very clear. Not everything has a clearly defined physical feedback that everybody agrees on. So, but nonetheless, this helps the machine learning do a lot better. The other, which you might have heard of more, is deep learning. What deep here means is deep neural networks, meaning more and more layers, many layers of neural networks. Unfortunately, when people hear about the word deep, you don't know how many times I heard people tell me, this AI has deep learning. They think deep as profound. It doesn't mean that at all. Of course, deep gives it more power. What it is again, think about you're trying to recognize image. At the lower level, you only have pixels, you have some color, you have whatever. Then you start combining that. The next level, maybe you have certain type of local objects. Is this pretty uniform? Is this different? Very much contrast in this area. So then they feed into each other. You're putting more and more a better feature, more meaningful feature together. And then you start going, maybe you will back off and say, Am I still doing pretty well? Is there any correction I want to make early on? You can go back and forth. So there's a lot of computation involved to do things like this. And so this can help the machine to overcome something in our field we call a vanishing gradient. So let me give you an example on what vanishing gradient means. Um, let's start with gradient. Some of you have studied enough math, you know what the slope is, but you don't even need to know that in algebra. Let's just think about what if I ask you to do a game? In this video game, your objective is to find the highest peak. And there are no paths, there are no map. You need to find the highest peak. And okay, how do you get there? Fast. Your goal is get there fast, then you win. Well, you will look at a gradient. Gradient meaning you, at any point of slope, you look around. Am I on the steepest slope? If I'm on the steepest slope, the chance for me to get to a peak is faster, right? You don't want to go around and wind about way and other people already get there. So that's the way you want to do. That's the gradient. You're looking at a gradient to climb up to the top of the hill. But it's not all that necessarily that simple because you climb up the hill, then you find, you know what, this is not the top of this whole region. This is just a local hill, local peak. There are other peaks. How do I get to another higher peak? Sometimes you can't even see. How do you know this is the top peak? You need to go down a little bit, explore a different area. Maybe that gets you to a higher peak. You sometimes even need to go down a little, then climb up. So this is why am I using this as example? In terms of how machine learn how to do a task, you can think about two ways. If you think of it as finding the maximum, that's going to the peak as fast as best you can. That is, imagine the peak is your target. How close are you as a machine to that target? The opposite way you can think of is finding the value, the minimum. That is, you can think about what is the minimum difference between what you want to achieve and where you are. So either way, the analogy is the same. So the vanishing gradient means if your computation is not so good, you often go in circles. You can't see which is a better way to go, which is a steeper gradient you should pursue. So in terms of computation, these problems are solved. But hopefully this helps you understand how AI, in terms of using machine learning, is going about this. So I only have two slides, and there'll be time for questions for sure, and discussion. So let's get back to robotics. Robotics, I don't know you have spent time thinking about this. It really requires multidisciplinary contribution. It's not all about computer science. I'm giving just some examples. There are really many more different areas, different disciplines can contribute. So in terms of computer science, we spend time talking about AI. There's also communications, right? The internet, the intranet, all that. Cybersecurity, how you keep it secure. The hardware architecture, do you have to build a special purpose computer just to do certain things? And engineering side, mechanical engineering, which you can easily understand. Many of your coaches probably come from this background. Electrical engineering, and how do you wire these? And also on the pure electrical, not so much electronic side, battery is a major challenge for many different applications. The battery lifespan, how safe the battery is, and how it transfers the energy without losing as you string together different batteries, and chemical engineering, material science. If you are going to get a robot outer space, what material do you think is best suited? And that involves a lot of these mathematics. And you are studying math, and maybe your not all your teachers give you a motivation why you study all this math. Of course, math itself is fun and interesting, but there are a lot of applications. Most of the math has great applications. In terms of robotics, some of you, if you're senior, you may have studied there is a Cartesian coordinates, the x, y you draw, right? There's also polar coordinates. Why do you need that? Think about if your robot move from point A to point B, it's easier to just use Cartesian. You go 3 steps this way, 5 steps that way. But what if your robot has an arm, needs to rotate, needs to reach out, do things? The rotation, if you don't have polar coordinate, you want to do this in the Cartesian way or vice versa, it's very hard. So there are a lot more mathematics needed than my simple examples here. There's also human factors, human computer interaction, and when you play with your robotics, you're on the team. Would there be time you wish you can easier program your robots to do certain tasks faster and combine certain tasks so you don't have to tell the 3 steps and when you're in a competition you want to get there fast but you have to tell the step by step can we combine these steps and go right there and how easy it is to do that and think about more complex self-driving vehicle self-flying vehicle the human factors, human computer interactions is a lot more complex and harder. And also application domain knowledge. And if you think about self-driving vehicle, it needs to know traffic law. It needs to know priority, a lot more things, right? And think about flying vehicles, even more complex. You need to program all this in. And how do you program this in? In the sense of deep neural networks I explained. That is not easy. And also, there are just a lot of challenges. Okay? And when you need a higher degree of autonomy, for example, you send this robot to outer space or deep sea, you can't keep interacting with this robot. There are just more challenges. So people tend to think, gosh, we have all the computing power. Today, my phone is more powerful than Atari or the first generation PC. That's all true. That doesn't mean this computing power is suited to do some of these tasks. And you can load all the, we today, cloud computing, a lot of the computation done in the server. We have factory of servers, server farms doing this. But if you send something to the outer space, you can't keep reaching back for data, for things to do, then send back the information. You just can't do that. Not even on an airplane. The communications are an issue, the computing power is an issue, the time is critical. You need to decide what to do first, what not to do, what to update as you have time. And also how robots, between robots, how they interact, and how robots and humans should interact. That's not some subjects study enough. There are people studying, but it's not the center yet. It's not center enough. So for those of you, you are not thinking, I don't want to get into computer science, engineering, any STEM area. You still, it may not occur to you. There are a lot of contribution from other other fields like economic theory and game theory. And let me give you an example on why some of these are highly useful. If your parents are driving around, say, hey, we're in this new area, we need to go get some lunch. What's the best place? Hey, get out your phone, search on this. Imagine you have a robot try to find a parking spot. Guess what? Your search engine today will send all of you to the same parking space or send you to the best restaurant based on recommendation. Guess what? If everybody ends up there, your experience is not going to be good. You have long wait line, you can't get in the parking lot, etc. So there's some sort of economic theory. Think about if you have hundreds of cars riding on the same road. They're all automatic driving vehicle. You don't want them all end up in the same place. There needs to be some trade-off, economic theory and game theory, how they cooperate to benefit everybody. So those are areas, even not in the STEM area, there are a lot of contribution required. So my final slide. So has AI done it all? Not really. we're making huge progress in this field. And personally, I'm one of the fortunate being in this field this long, since the 80s, and how I watch it grow. And there's a lot of hype. I often have friends send me, gosh, such and such as is a new software. What it can do is it can read intention. It can read your human mind. Nothing like that. What it was in this demo room. They give them glasses. They go in and look at different things. And this I know what you're thinking. How do they know? No, they don't read minds. But the glasses, you can easily track the focus area. As I'm tracking the focus area, the AI program can figure out what is your interest. Because as you go into a new room, where what attracts your attention, you spend more time looking, tend to be what you're thinking. That's all. Does it read mind? No. So watch for hype. And today, as I mentioned, there's no single AI solution solve all the problems or even enough of the problems. It doesn't exist. They're all individual solutions. And the best natural language processing, I'll give you an example, and it's local. Some of you may have heard of Paul Allen. Paul Allen is a co-founder of Microsoft, as Bill Gates. They started this together. And Allen, before he passed away, he spun off this company called Allen Institute for AI. The short name is AI Square, AI2. And I certainly know some of the key people there. And it took them, started about 2002 or so, because our organization are a larger organization. There are people working on that from Boeing side as well. And try to read eighth grade science textbook and try to pass it. It says it's science exam, but basically it's biology. Just read the text. Don't worry about the diagrams, the illustration diagrams. Don't learn anything from that. Just read the text and with AI. Understand natural language, process it, represent it, and there are many world teams that participate in building this. It took well over 10 years. It could barely pass the eighth grade science exam. It's multiple choice, so you don't even need to write essay. It finally is getting to a point it's doing really well. Think about this is one subject, it's one type of text, and it took this long, this much effort to do. And you can check into it more. Maybe there's something you like to explore as your internship, whatever. And it shows you how hard the problem is. And also, there's a trade-off between interpretable and non-interpretable methods. Um, what does this mean? If I ask you, how do you know this image, the top one's Julia, the bottom one's Anne? How do you know? I rarely ask this kind of question, right? I may ask you, how do you know this is a picture of a cat, not a dog? You say, well, look, this is smaller, the ears are different, whatever. For human pictures, you really will ask, how do you know? So some problems, you don't need an explanation. You don't need it to be interpretable. And that's where deep learning is good at. Working on this low level, detail level, and find you some solution. But if you're doing engineering work, our engineers need reasons, need explanations. If you have an AI program saying, okay, I predict this area, we're going to have so many defects, engineers will say, why? What caused the defect? If I don't know what the defect is, what can I do? And this is a big argument. There are definitely professors and researchers and believe if you have a better AI program tell you people really is likely to get cancer or not, why not use it? Well, personally, I don't agree because so it's better. If you don't know what caused that, what do you do? Cry? You need to know what are the reasons for this AI program to reason that. So you can change your lifestyle or you can change certain things, your environment, so you avoid that or you defer that cancer growing process. If not, just knowing it supposedly overall, you know it more accurately, is that useful? So this is highly debatable. And I already mentioned lack of knowledge, and especially common sense knowledge. And also, not all problems are well suited for AI. You have to ask whether you know enough about features and variables we can use interchangeably in a problem. Again, for example, does AI do well in embedding stock market? Not necessarily. You can use this as a reference, but what are the features? The world is big. Economy, the weather, unemployment, the local traffic, too many factors can impact that. If you don't even know what are the variables or features, you can make an AI program do this very well. Um, if you draw with lots of not so useful features, it doesn't help either. So, and you need lots of data and focus on the focus task. Lots of data is not necessarily easy. The outer space situation, how much data do we have? It's not like we're going there every day. With different environment, we collect the data. You don't have enough data to learn from that. And vehicles are the same. There are not enough accidents to learn what caused those things. So also more AI applications. You will see more and more every day. And in every day and in definitely in aviation, which I spent vast majority of my career in. And but the use of AI will also change other technologies and the total system from the system engineering perspective. If we have tons of drones flying, gosh, you need to worry about so many different things. It's not just worry about your AI created drones and how do you manage the traffic. It's very different from today. And also, how do you get certification and regulation? There is no clear path. You probably at least heard about how to get a car certified. And so the self-flying airplane, there is no clear path how to get there yet at this point. And finally, again, there needs to be more understanding study the interaction between AI and human intelligence. And we're good in different things. The AI, like in all machines, are very good in tedious, routine work. They can repeat it and not getting tired. But maybe some boundary cases where a human can step in and do the hard task and do it fast and do it well. And human is very good in tolerating inexact situation and incorrect partial information. So with that, I will stop here. And any questions or discussions?
All right,
All
great.
right,
Thank you
great.
so
Thank you
much.
so much.
Um,
Um,
I can hear myself.
myself.
But we have a couple questions here. The first one
Okay.
is, what kinds of AI projects have you created or contributed to?
Sure. Yeah. That's a great question. Since I spent 30 years in Boeing, so I just use Boeing examples, and several of the best known. Um, One is we're the first to use mathematics representation of natural language and make it a representation you can visually see topics related. A bunch of, if you read internet, bunch of documents, what are related topics were the Pacific Northwest National Lab did the visualization part. My team and I figure out the mathematics and what are the topic relatedness. And as you zoom in visually, you can see these are the topics that are similar, you can explore. And the project, the visualization tool is called Starlight, Light, Starlight. There's a Wikipedia page you can see. That was what we did in late 90s. More recently, inside Boeing, my team and I launched a very comprehensive engineering search capability. There is a tool for the government side. There is one inside Boeing. It's called OPHATS, OP-HATS. What OPHATS does is use a combination of, again, visualization and natural language capability to help engineers search all sorts of engineering data, but that's not the same as Google search. Google search will give you a variety of things you can explore, but not in depth and not finding the related from engineering design to manufacturing to customer support, maintenance, and peak time. There were about 8,000 users of that tool. And there are other variety of things related to maintenance and aviation safety, how we look at a lot of data to tell what seems to be the overall theme of repeat and maintenance issues, etc.
All right, interesting. The next question is, how has AI been used as a tool during the pandemic?
I'm not sure there's specific things about the pandemic, but AI was definitely used to solve certain disaster relief. How do you identify, again, from the free text or social media side, how do you identify emerging issues for any kind of disaster and disaster relief, how you coordinate that? And also a different type of application would be search some missing uh, Air France, I believe, has got lost, crashed and lost in the ocean. Again, very rare events. It's very hard to study, but AI was used to help identify the exact location, and they did find the whatever's left in the ocean. And pandemic area, we're looking at these correlations, and but I'm not sure. I'm not personally, maybe because I'm not in that medical field. I'm not aware of specific groundbreaking results using AI.
All right. The next question is, do you enjoy working with symbolic processing or neural networks more?
I have done both, and the trick is how you combine both. The symbolic processing side, like I said, what people recent years, the neural network side has grown so much. But what needs to happen is to do real application, you have to get back, combine both. The neural network side, the deep learning, allows you to process so much more data. But on the other hand, that's easy when you don't need domain knowledge. But when you have domain knowledge, you can do a lot better. And I have patents, US patents with my team, how to combine linguistic knowledge with machine learning neural networks processing. For example, how do we identify in a lot of text data what's a part? Because we know for English, the parts, what kind of something something unit, something something valve. The valve, the last word, the last noun in the sequence of noun is the ground part of that part. The others are descriptors. Once you figure that out, we can use less machine learning power but more linguistic knowledge and combine it. And so the trick for everybody to build real application instead of writing some papers on new machine learning methods, if you want to build real application, the trick is how you combine it and combine with your human computer interaction together.
Wow. All right, that makes a lot of sense. Okay, the next question is, usually how many trials do you usually have to run before the AI starts to learn, and how much processing power does that usually entail?
You can do it definitely on your home computer, personal computer for reasonable size problem. Not enough to send you to the outer space for sure or deep water. But for any real size problem, this might be enough. Or you have work computer, you have university computer, that's enough. But as to how many tries, depending on how good your data is your data representative enough? Right? That's another letdown in industry. And people say, oh, gosh, I can predict this, I can predict that. Well, you got some old data, 3-year data, you built this, and your customer turned out, gosh, it didn't work. Guess what? Last 3 months, because of last 2 years, because pandemic, oh, your data is different. People's shopping habits change, all that. If your data is not representative enough. You build this, it learns the wrong thing. So how good your data means how representative it is. It represents both many different cases, and that's also important. Otherwise, you try to find defect, like I said, you have very few defects. You can pour 10 years of data, but there's so few defects, it's hard to find what represents the defects. So it really depends as to how many trials, and that again is an important question. How you design this, how you design a fair test. And typically we do recall precision. Recall means out of the correct answers, how many did I get right? Precision means out of the ones I got, how many correct? So that's recall and precision. It's a trade-off. I can say everything fits this case. Well, I get everything right, but I got lots of wrong. Or vice versa. I get very few, they're all right, but I miss none. How you design this in a fair way fits your application. Once you design this, and you don't always know all the correct answer. If you know all the correct answer, you're already done, right? So you have to design a way to sample these and build some smaller case. Say, okay, do I believe this represents the larger data, and measure that way? So that there's a lot involved, not so much on how many iterations to run. And typically, some of the cases we run probably 7 iterations. Once you design all these, what I'm saying correctly, 7 iterations. We have some papers. You can even see some of our published papers on how to identify part names in IEEE conferences. Typically, 7 iterations for those problems. We are already getting reasonable so-called conversions.
All right. The next question is, what do you think is the most impressive or complex thing that machine learning can currently achieve, and how advanced do you think this technology can get in the future?
That is a great question. Not sure I have a great answer. I would answer it based on my background. And if we can continue going the self-driving/flying vehicle, that will go a long way, really impact. Since I'm in this business, right, we always say that brings people closer together. That changes society in a major way. So we can better explore the outer space and deep ocean and have a reasonable way managing what are the self-driving vehicles, what are human driving vehicles and airplanes and drones, all that. If we can better manage all this, not just from a technology point of view, but like I said, there's also economic and everything. I think that would really change our era, our next 30, 50 years in a very significant way. But there are definitely a lot of other breakthroughs, whether it's imaging, analysis, identifying cancer, all that. There are a lot of important things to do.
All right. The last question is, how much AI is needed to create a virtual reality game?
That's a great question. It may or may not be that much because the game involves a lot of things, and because you need that user experience, so a lot more is involved. Your user experience, not necessarily you have the smartest AI will give you that experience. There's a lot more involved. The novelty, the how good, how easy it is to use, how ergonomic it sounds. So a lot more is involved. And this is why emphasize the system engineering system type of view. You have to look at all its totality. You don't want to just only focus on how smart it is. Smart it is only one aspect. That doesn't necessarily make the best experience or best game. You want novelty. You want aesthetics. You want a lot of things that work together.
Yeah, it's a really good take. I think those are all of the questions. Thank you everyone to come. Thank you everyone for coming, and a really big thank you to Anne for taking the time out of her day to come and speak for us. And Anne, if you have nothing else to say, I think we can just end this broadcast right here.
Sure. Thank you, everyone. Enjoy your weekend. Feel free to contact me in my email, and Julia can download the slides and can share, and you can download as well. Thank you.
All right.
Bye.
Thank you, everyone. Bye.